Take a look at question 3. Question 3 says, we have a model for population PT. PT in a suburb of a large city is given as initial value. Problem as follows. We have dp dt equals to p times 10 to negative 1 minus 10 to negative 7 times p when p is 5,000. The population, initial population is 5,000. And t measures in months. Well, question says, what is the limiting value of the population? And at what time will the population be equal to 1/2 of its limiting value? At what time the population is equal to 1/2 of its limiting value. Very good. So first of all, remember that we have autonomous differential equation. dy dx is equal to f of y. It means that we don't see any free variable appears on the right hand side. On the left hand side, you just have the derivative, the rate of change. Very well. So first, we want to find the critical points. It helps us to find the stationary or equilibrium points. We take the derivative and set it equal to 0. So this is our derivative here. We have p prime, which is p. Let's simplify this. We have 1 million minus p divided by 10 to 7. So set the derivative equal to 0. P is 0 and p is equal to 1 million. Now let us take a look at our slope fields or analyze the phase line. Where does the limit take us? Since our applet is written in x and y, so let us make the necessary adjustments. Here we have p times, which is now y times 1 million minus p minus y divided by 10 million. Okay, let's graph this. Let's just increase the y values. And x is given in months, so we can change it to 10 months, for example. Let's analyze the behavior. So around 1 million, this is the behavior that we see in the slope fields. As you can see, they are converging to 1 million. On the vertical line, vertical axis, we have our phase line for 1 million. Just take a look at this. You can click on more of these slope fields to see the behavior, to see the relation. But around 0, you see the graphs, the curves are diverging. So it seems like for our slope fields, if we look at the slope fields that we have, T, P, around 1 million. The solutions are converging toward 1 million. So solutions are converging to 1 million. What's the meaning of that? It means that if we take the limit of the population as t goes to infinity, then it converges to the line 1 million, or the value is 1 million. Let us solve this differential equation. To solve this differential equation, we have the following. We have dp dt equals to p million minus p divided by 10 million. So here we have dp divided by p, a million minus p equals to dt over 10 million. So let us take the integral of both sides. Now let me erase right-hand side of the board. This becomes the integral of dp over p plus dp over 1 million minus p equals to the integral dt. So I'm borrowing a million divided by 10. This becomes ln of absolute value of p plus, we get a minus sign, ln of absolute value of 1 million minus p equals to 1/10 t plus c sub 1. So ln of absolute value of p divided by a million minus p is 1/10 t plus c sub 1. So p over 1 million minus p is e to t over 10 times e to c sub 1. Remember that you have a plus minus sign, so your population can be isolated on one side by using some simple algebra. P is equal to c e to t over 10 times 1 million minus pc e to t divided by 10. So p is equal to, if we bring p to the other side, c 1 million e to t divided by t, 10 divided by 1 plus c e to 10 over 10. Very good. So this is So by solving the initial value problem, the model becomes Pt equals to, well, what do we have? We have 500 divided by 5 times 10 to the negative 3 plus 995 times a 10 to negative 4 e to power t divided by 10. So this is our model. And we know that the limiting value is 1 million. So how long does it take that the population reaches 500,000? So 500,000 is equal to P of t. By solving for t into the equation, t becomes approximately 53 months. So in 53 months, the population gets to its half of the limiting value.